This video is the first in a series of videos where I study sideband noise in oscillators and in the components we use to build oscillators from. It is a continuation of the work that I have described here. This oscillator, which provides, I don't remember exactly, something like minus 180 dBc per hertz. This work is motivated by my interest in studying frequency multipliers. So in order to do that, I built this unit, where you can see I have 6 transistors in parallel. There have been crystals here, and I had difficulties with this. First there was a transformer here, and there were some peculiar sideband noise oscillations of some kind. So I decided, well, that could be parametric oscillations due to the ferrite. So I changed the output for iron-free. That didn't help. Then I decided maybe it is the capacitance of the transistors, the output capacitance, that could cause parametric oscillations. So I skipped this. To eliminate varicaps, I made this thing. There are 6 PCC88 tubes, which means 12 triodes in parallel. And then I send that is in grounded grid configuration. So the input impedance on the cathodes, all the 12 parallel cathodes, is low enough to fit the impedance of the crystals. And it runs at a fairly high power, and there are no parametric effects possible in this. The vacuum tube amplifier has a crystal filter. And as you can see here, with 1 kHz per division, the 3 dB bandwidth is something like 2.5 kilohertz. And the input impedance is 50 ohms, pretty accurately. The crystal filter can also be set to use 2 sections, and I switch. As you can see, the gain is very much the same, but the 3 dB bandwidth is about half. But at 10 kilohertz, the attenuation is much larger. I switch back. It goes from about 8 dB down to something like minus 30. And the input impedance is 50 ohms in both cases. Now I'm looking in the reverse direction through this tube amplifier, and you can see the attenuation is 20 dB, and the output impedance of the amplifier is very close to 50 ohms. And this is with 1 section of the crystal filter. Now I change to 2 sections, and as you can see, at the center frequency properties are the same, but the selectivity is much larger. This is a low noise, modest low noise amplifier with 50 ohms input impedance. I'm testing the noise figure of it with this noise head from Magnetic, and I'm looking at the perceuse. The amplifier is connected to the perceuse, and with the noise source off, I have minus 119.7 dBm. Now I switched on the noise source and I have minus 116.7. Well, not quite, but close to it. Maybe 0.1 dB less noise would be appropriate. So 0.1 dB, it means the noise figure is 5.7 dB. This means that the noise floor now, with the noise source off, is at minus 168.3 dBm per hertz, because room temperature is minus 174, and subtracting the noise figure we get 168.3. Now I connect the output of the amplifier, and it's clear there is no noise coming out from the amplifier except very close to 10 megahertz where there is a low impedance on the cathodes. On the maximum here we have about 10 dB noise, but only very close. The noise floor is minus 118.8. So the amplifier, the white noise floor of the amplifier is very low because there is feedback. I mean, it's a grounded grid amplifier and it doesn't produce any noise on the output side when the impedance on the cathode is high, which it is outside the resonance of the crystal filter. This is with the 2-section filter, and I can connect the 1-section filter, and the difference is small. I'm now sending minus 32 dBm into this amplifier with the tubes, and I'm looking at the perceives. And I increase the level by 1 single dB, and you can see the AD goes into saturation. So I have to go back to minus 32 dBm. The frequency is about 10 kilohertz away, and the noise floor is now minus 111. And when I switch off the signal, the noise floor goes to minus 114. So that is 3 decibels. With the single section crystal filter, the noise floor is a little bit higher. So some noise comes from the signal generator. This is a notch filter. I inserted it between the tube amplifier and the low noise amplifier in front of the perceives. Still running minus 32 dBm. And then with the signal on, I see minus 114 dBm, and I switch off the signal. And I still see minus 114 dBm. With a 25 decibel stronger signal, what I see on the perceives is like this. and the noise floor is minus 109. I switch off that signal generator. And then I see minus 113, 114. So the signal is a little bit too strong. It gives more than a 3 dB degradation. Now, probably it is the sideband noise of the signal generator. I switch it on again and go for the single stage crystal filter. And you can see the noise floor is much higher, very much higher. And for some reason it's also very much higher when I go back to the two-stage filter. Seems I have a problem with that switch. But I did switch it many times, so it came back to the original performance. I'm now at a separation of 50 kilohertz, and I switch off the signal to get the noise floor, and it is at, I think, still minus 114, and with the signal it comes at minus 113.1. So it's a 1 dB increase of the noise floor. And this is with an input signal of plus 7 dBm. Which means that the output has to be something like plus 15 or so. I don't remember the details. Anyway, if I increase by a single dB now, well, one more dB and one more dB, there are some funny phenomena coming up. These are noise oscillations of some kind. If I click on one of them, you can see it's not a sine wave, it is a noise hump. This is something that I previously attributed to parametric oscillations in ferrites or capacitance diodes or whatever. But it happens also with this setup where there are no such components. I bring up the signal level a little bit more. And now we see in the close range there are more oscillations of some kind, noisy oscillations. And they vary very much with the signal amplitude. Now it's plus 14, plus 15, plus 14, plus 13, plus 12, plus 11, 10, 9, 8, 7, and now they are gone. What is this? I added 6 decibels of attenuation between the amplifier and the notch filter. And then again, look here. And the level is now plus 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, that's the limit of this generator. And I see noise. It's now minus 100 dB, but I don't see the oscillations. I switch off the generator, and then the noise is much lower. So, conclusion, those oscillations come from the notch filter, the crystals, but the wide range noise comes from the attenuator, perhaps. Now, minus 113.7 with the signal present, and I switch it off and look for what will be the new. (114.4). That is 0.5. That is 0.8 decibels increase of the noise floor when I'm switching the signal on. The power level is plus 17 dBm. That's at the output of this amplifier. With the noise head at the notch filter input, I have to set the noise figure to 1 dB to get the same noise floor, 113.7. That means that the noise at 50 kilohertz is minus 173 dBc per hertz. That means that the sideband noise level at 50 kilohertz is minus 190 dBc per hertz. And the reason for it, I don't know, but this is the limit given by the notch filter. So first I have to make a better notch filter. Here is the frequency response of the notch filter. Standing wave ratio is very good near the notch and some 10 kilohertz or more away from the notch. The span is plus minus 50 kilohertz. Attenuation is very low, a tenth of a dB or less. But on the notch it is very high. But there are some sideband noise issues in this unit. I'm now running at plus 7 dBm, which was a safe level. But now I have inserted a unit with a crystal. And I'm using groups of parallel crystals with the same resonance frequency, various places to allow more power. And in this case I have a transformer to bring the impedance down to 12.5 ohms, that is to make more current. And I'm looking at the current through the crystal with this current probe, and this is what I see, about 100 millivolts peak to peak. That is 35 milliamps RMS, or about 4 milliwatts distributed over 5 crystals. So less than 0 dBm per crystal. Problematic. Now I'm testing just one of those crystals, and the problem has disappeared, and the current is very close to the same, but just through a single crystal. This is another crystal. It's still the same level on the signal generator, but it changed itself. Now it came back. You can see the noise that it generates, and I do some tuning on it. And look at the current through the crystal at maximum current. It looks like this. So, well, there are some extra spurs that come from me holding the screwdriver, but here is the noise peaks due to chaotic behavior in the crystal. So this is a bad crystal. This one is really bad. Here you can see, and it was much worse very recently. I tuned the series capacitor. And you can see we have this false noise things on the upper side, and also some noise close to the carrier. So I have to put this aside. Here is another crystal that isn't good. You can see something is happening inside the quartz. The current is the same as for everyone else of the crystals, and most of the time it behaves normally, although there is this little peak here. I could see something was unstable, but now when I continue to knock at it, it is no longer so. But I have seen a problem with this one. So I think it's better to not use it. Some more crystals on the notch, while rejecting those that are particularly noisy, have a little bit better performance. The performance of this notch filter is not much different. It's not as symmetric here. I didn't care to tune that in detail, but the loss is very low, 50 kilohertz on each side, and SWR is very good on the carrier frequency as well as 50 kilohertz away. Now the signal level is 3 dB higher, and I don't see those noise sidebands anymore. They will come if I increase the level above this that I have now. The noise floor is at minus 113.2 dBm, and I switch off the signal. And the noise floor is not very much different, 1 dB. So I switch on instead the noise source here. The noise source is connected directly into the notch filter. So I'm measuring the noise floor at the same point as where I was measuring the noise floor of the output of this vacuum tube amplifier. And the level is, can you see it? Minus 113.2. And then the noise temperature of the noise source is minus 172 dBm per hertz. That's 2 decibels above room temperature. I'm looking at the output of the tube amplifier on the spectrum analyzer, and I find that the power level is 19.5 dBm, plus 19.5. This means that the current noise floor at 50 kilohertz is minus 191.5 dBc per hertz. And part of it is due to the analyzer, I mean the notch filter, and part of it is due to the amplifier. I am now using Linrad instead of the Perseus software because I have much better S-meter things, the S-meter graph here. This is the noise floor 50 kilohertz away from the carrier, and the noise floor doesn't look quite right. It looks like there is a stability issue of some kind. So I make some vibrations, and indeed suddenly it's better and it's unstable somehow. Now it's really bad. I try this switch. Oops. Aha. I'm going back and forth with the switch. Seems I have to replace the switch, or maybe go without the switch here. This is the problematic switch. It says KNX2 and 3 amps, 250 volts AC. I have replaced the switch, but there is obviously a stability issue still in this unit. So I bang on it. Oops. Now it's much worse. So I change the new switch from position 2 sections to 1 section, and of course I get much more noise, and then back to 2 sections. Seems like the problem is still the switch. This is another one, but I go back and forth with it a couple of times. Well, this doesn't seem really very good. Anyway, the noise floor I have can be as low as this. That is minus 85.36. Now I connected the noise source and set it for the same noise level, minus 85.36, well 34, but it is very close. And the noise figure, the noise temperature is 6.3 dB. That's minus 174 plus 6.3. That's at the power level of 19.5 dBm. So the dynamic range, the sideband noise level is at minus minus 174 room temperature plus the noise figure minus the power level 19.5, and that comes out as minus 187.2 dBc per hertz. So it's not quite as good as I saw before, and I don't know the reason. There is something that isn't quite stable in this system. The amplifier has an output here, an amplitude limited output, which is intended to be connected to the input to convert the amplifier to an oscillator. And this is what I have in the instability. Now I replace this one with another one. Means another 50 ohm dummy load. Well, this was not very good. I remove it and leave that output open, and then things look stable. So a 10 dB attenuator, and then this one, the old attenuator. And I have to wait for a while to see whether things are more stable now. That dummy load was a problem. The noise floor is less unstable now, but it is not perfectly stable, so there are more problems. The level is minus 86.95. To get the same level, I have to set the noise source to 2.3 dB above room temp, and that gives me minus 86.97. The signal level is still plus 19.5 dBm. So after replacing that dummy load, I now see minus 191.2 dBc per hertz. So this is good enough for studying some other components that we use when making oscillators. There are, of course, problems within these units I have, but to understand what the problems are, I have to study the different building blocks that go into a design like this. I have added 12 dB of attenuation, 6 dB plus 6 dB, and brought up the signal level a little bit. And now I see these parasitic oscillations. Well, I thought, that is, it comes probably from the crystals in the amplifier. This one, and also this, which is some kind of noise oscillation somewhere. And I click on it just to show that it is not a spur of normal type. And you can see on the waterfall it fluctuates. So I go back 50 kilohertz away where I do this typical measurements, and now I bring the signal level down in steps of 0.5 dB. One step, you can see the frequency is changing, and this one went down considerably, half a dB less, and this is gone, and this one is stronger and closer in frequency. And then another half a dB. So this oscillation is coupled to the signal amplitude. I am now at 12.4 here, and I go up 12.9, 13.4, 13.9, 14.4, and it seems that the oscillations go away when the power goes even higher. So I will remove the attenuators now, and what I see is very similar, but I see it much better. Of course, I mean, there's 12 decibels more signal. So I step down again in steps of half a dB. 12.9, 12.4. And there is an abrupt change. Well, an abrupt change here that you can see here as well. And that signal. And one more step. This is now very weak. And here it seems to be gone. That's 9.4 dB here. So I go up again, and we can see how these phenomena start. So this is the level where I start to get problems. And on the spectrum analyzer I can see this is 21.5 dBm. I have converted this amplifier to an oscillator now by taking the limited signal from here and moving it to the input. And this is what I see. It is not perfectly stable. I think it's due to the crystals, but I don't know. I now switch from the two resonator crystal filter to the one with only one section. And you can see the noise is much higher. So, well, that's interesting, at least. The power level is pretty high. I have to put an attenuator here. Because otherwise I'm putting the spectrum analyzer at risk. So the power is, well, 26 and plus 6, that is 32 dBm. And that is with the two-section filter. And with a one-section filter, the power is now 29 dBm, plus those 6 of the attenuator. That means 35.5. That's 3 watts or something. Maybe I'm putting the attenuator at risk now. That could explain why the noise went so much higher. With the attenuator in place, having 29.5 dBm at this point, which is the input of the notch filter, this is the noise floor I'm observing. Something like -77 on the Linrad scale here. I have not calibrated it at all. To get the same noise level with the noise source, this one, I have to put it to 17 dB. It's on the high range here. So it is 17 dB above -174. And that gives me -186 dBc per hertz. So it is a little worse than before, and the reason is probably noise in the crystals, but could be anywhere else. So I will spend some time trying to improve on this. This is a band pass filter with a notch about 20 kilohertz below 10 megahertz. And this is the characteristics. The loss at 10 megahertz is 0.28 decibels, and the depth of the notch is nearly 40 decibels, or maybe even a little bit more. I have inserted that notch filter in front of the notch at 10 megahertz to investigate from where I get noise sidebands. And it's of course possible that I can get sidebands from this unit also, or from connectors or whatever, but some conclusions will be possible. First of all, looking here, I can see these noise variations that are not present in the notch. So they come from the amplifier. If I switch off the input signal, the noise is something like 3 decibels lower. So there is a noise contribution from this notch filter, or perhaps from this unit. Now I increase the power in steps of 1 dB. 1 dB. One more dB. One more. One more. Here suddenly the amplifier gets a problem. Maybe the crystals. We have these oscillations that probably originate in the crystals. And now suddenly there was a big jump in the noise at the center of the notch. This must be noise generated by either this one or that one. When I go back again, 1 dB. So there is a threshold here where something starts to generate a lot of noise. I increase 1 more dB. And 1 more. and that doesn't increase the noise. So I go backwards, and again, and here something happens. So there is a specific power level at which something goes wrong, here or maybe here. I need a 6 dB attenuator to protect the spectrum analyzer, and with it in line I can see plus 27 dBm. So the level where this noise problem happens is 33 dBm. This is the schematic diagram of the 10 MHz notch filter. Input here, then there is the crystal, which has a very low impedance on 10 MHz because it's several crystals in parallel. Then there is a 54 ohm resistor, and finally a capacitor to tune this thing for a resonance at 10 MHz with a series impedance of 54 ohms, or maybe 55, there is some also in the crystals. Then there is a quarter wave transmission line with lumped components, and then there is a second crystal which is tuned to the same frequency. Presents a very low impedance here, means that from this transmission line the impedance is very high on the notch. So on the notch the only thing that is visible is this resistor. And then there are transmission lines and more notches. Now the level is low, so there's only one or maybe two crystals here, and then there is still another one, and then there is a final link to fine-tune the impedance, because I want 50 ohms and a very low loss through this. Now, if there is noise here, what I can suspect is maybe this resistor is noisy. It's composed of four of these ones. I don't know if it is easy to see. It's 51 ohms, rated 1 watt. I think they are metal oxide. 4 of them, parallel and series, to get 51 ohms. And in series with that, one of these resistors, and I don't know, 2.7 ohms, and what kind of resistor it is, I don't know. Could be carbon film even, but it could be metal film, I don't know. This is what it looks like inside, and what I suspect to be a problem is these resistors, and I see now it is a 3.3 ohm resistor here. I wanted 50 ohms on the input, of course. And I will replace these ones for something else, but it has to tolerate at least 2 watts. I now put a 50 ohm microwave termination for the load. It's not 54 ohms, but the difference is very small, so it doesn't matter now. And I have this at 4 dBm, and I look at the noise within the notch. There is some instability in the oscillator, but as you can see, it doesn't affect much the signal within the notch. But I increase the amplitude in steps of 1 dB. 1, 2, 3, 4, 5. Not much happens. 6. No, a lot happens. 7. So at the same point, that was plus 11 here, the noise goes up dramatically within the notch. And since I don't think this resistor is the same performance-wise as the other set of resistors, I have to suspect that the problem is due to the crystals. Some simple math. 2 watts on 50 ohms means 0.2 amps at 10 volts. 8 crystals share that current as 25 milliamps per crystal. They are about 10 ohms, which means that 25 amps will give 6 milliwatts, that's plus 8 dBm per crystal, and they are rated 0 dBm. So this notch filter must not be used at power levels above about 1 watt, or maybe even a little lower than that. I have inserted now this 3 dB attenuator at a power level of 0.5 watts, and it's rated well above that. And what I see on the screen is this. In the notch, the noise hasn't increased, but outside the notch, the noise has increased dramatically. This attenuator produces severe sideband noise. It's probably AM noise. I'm looking now outside the notch with the S-meter, and I take this 2 decibel attenuator and insert at the 0.5 dBm power point. It attenuates by 2 dB, so one should expect a lower noise, but the noise increases by about 1 dB. So this one is also a noisy attenuator. Now I inserted this 10 dB stepped attenuator. It looks like that. Not so nice. And I change it from 10 dB to 9 dB. Oh, then it's good. 8, 7, 6. And now it's 0 dB. So this one has a bad connection when set to 10 dB attenuation. I probably would have to switch it back and forth between 9 and 10 many times. I did that many times, but it didn't help. So this one is faulty at the 10 dB setting. And probably I wouldn't see it normally, maybe perhaps in the intermodulation measurements. I have cleaned the contact surfaces with isopropylic alcohol. I have increased the contact pressure also by bending some things. But still, this attenuator has problems. When I turn it to 9 dB, 8, 7, and so on, but 10 dB step, well, sometimes it's okay, but most of the times it's not. And I don't know the reason for this, but the conclusion is, don't trust your equipment just because it looks very professional. There could be some problem with it. And in this case, I don't know what the problem is. I have been using now the 2-section crystal filter in the vacuum tube amplifier, but I can switch for the 1-section filter, like that. And you can see the close range noise is stronger, but the wide range noise is a little bit weaker. That's because the power is a little bit lower. So this is the 2 section. And here is the 1 section. Now, do not care about the carrier because the frequency switches a little bit. So the notch is not centered at the same place anymore. I can click on it like that. And then this is the 1 section. And here is the 2 section. The 1 section and the 2 section. And it seems like at close range there are some problems with 50 Hertz. Don't know exactly how they get into the tube amplifiers. They have DC filament supply, but some minor problems with filtering, perhaps. With 12 dB attenuation and the 2-section crystal filter, the power level for the oscillator now is 20.5 dBm or 20.6. Well, here is the noise floor at a separation of 50 kilohertz. And I can read it out. Minus 82.6. This is an arbitrary scale, it's not calibrated in any way. Once again, 82.7. To get the same reading, minus 82.7, by use of the noise source, I have to set it to a noise figure of 5.7 dB. Means the noise floor is at minus 174 plus 5.7 dBm per hertz. And that's at a power level of 20.6 dBm. That is with the 2 6 dB attenuators and into the spectrum analyzer. That comes out as minus 188.9 dBc per hertz. What I have is some sideband noise caused by something inside this amplifier, and it isn't quite stable. I can see from the noise measurement here it doesn't have the white noise characteristics. If I remove the feedback and put the dummy load on the input, like this, the noise is much lower. And now I can remove the 12 dB attenuator like that, and you see the noise from the amplifier itself, its white noise is very low. It isn't visible here. So I have a sideband noise problem. Something is modulating the signal, and I don't think it's the vacuum tubes. It could be something else, and I will spend some time looking for it. The box is open with an oscilloscope probe, so I pick up a lot of interference. But nevertheless, at 50 kilohertz offset, the noise of the oscillator, or now it's run as an amplifier, is dominating. When I turn this trimmer, it doesn't look good, and the output voltage you can see here, it doesn't vary much. But the noise does vary with some small changes of this setting. So I have to replace this trimmer. I have changed the limiter in the output part that goes to the feedback to provide 1 watt output power, a little less than before. What I see on the Perseus is like this. I don't see the notch filter 20 kilohertz down, and that indicates that the noise comes from the notch filter, or probably from the 10 megahertz notch filter. I stop the oscillator like that, and then the noise is much lower. And I restart it. Now I'm running the single section crystal filter, and you can see here, and I switch for the 2 section filter. And the close range noise is a little less, but 20 kilohertz away the noise is the same. The power level is 29.5 dBm. I'm now running the unit as an amplifier, also at 29.5 dBm. Looking like this. With a single section crystal filter, this is what I see. There is a lot of noise from the Hewlett Packard 8657A, but with the 2 section filter it looks like this, and this supports the idea that the noise that I see actually comes from the analyzing tool and not from the amplifier with its crystal filters. Now, running as an oscillator, here I don't see any trace of the notch. Switching off the oscillator, and you can see the noise level is much lower. So this is not the properties of the oscillator, it's the properties of the analyzing system. 6 decibels of attenuation with an unknown addition of noise modulation from the resistors inside. This is what I see. It looks far more stable. And I can stop the oscillator and then turn it on again. And we see noise that is not on the notch. So something odd is going on here also. And everything is a bit microphonic. But anyway, with 6 decibels like this, the noise floor I have at the 20 kilohertz separation is this, and that's on the notch, so that's not of much interest. I go to 50 kilohertz separation here to get the noise floor. And then I connect the noise source. To get the same reading through the 6 dB attenuator, I have to set the noise generator to 8 dB noise figure. And then I see the same noise at 50 kHz separation. What I see now is minus 196 dBc per hertz. But that's not the properties of the oscillator, it's the properties of the crystal notch filter. So there is still some work to do on this.